right, my friends, we have so very little time and so much to get through. So as always, I encourage you to take note of this one slide, arguably the most important slide that you're going to see in this room in the next 2 hours. This slide contains a number of things. First and foremost of which is the code where you can find the example so you can follow along at your own leisure, at your own discretion later on. That code is there for you. It's for your own edification. I already know this stuff. I don't need it. I put it there so that you can, see what's what. Don't do it now, mind you. Take a photo, maybe a shot of the screen, but not actually a screenshot. Take a screenshot of that, and then use that later on, right? It will also have my coordinates. So, if you have questions, when ineluctably you have questions, don't hesitate to reach out to me. I'm here for you. I'm at your service. I'm happy, as always, to answer questions, and I'm available via any number of different channels. Not the least of which are Twitter. How many of you are using Twitter? I'm just curious. 2020, Twitter. 2020, Twitter. 2020. It's a new decade. The rest of you, what are you doing? Get on Twitter. Shame on you. It's 2020. It's a great place to be. It's the new IRC. It's where the developers that drive the open source that power your business are. So you owe it to yourself to be there. What about email? Who's using email? Anybody? No. Good. Moving on. I'm not a big fan of email, but I've had to soften my position on email in light of Slack. It's taken a considerable amount of work, but I've actually started to appreciate email given Slack. Now, I shouldn't kvetch too much. I have before me one of those newfangled 2019 last year models of the MacBook Pro with the 64 gigs of RAM and all that stuff, the SSD, top of the line machine. And now with that machine, with 64 gigs of RAM, I am now able to both run Chrome and Slack at the same time. It has taken a while, but we have finally arrived. So who knows, maybe in 10 years, maybe I'll love Slack. I don't know, anything's possible. It's a brand new decade, anything's possible, So there's that, there's my coordinates, find me there. My name, as always, is Josh Long, and I'm very happy to be here. You can see that I've got some other things out there. I've done videos, these are on Safari, these are different videos that you can find on Safari. It's like a technical marketplace for technical content, and all you can eat kind of buffet style subscription for technical content. So you pay one prefix per month, and then you get the whole thing. Lots of good stuff there. Actually, I've just done an updated version of Reactive Spring, and there's one in Kotlin that's you don't see it there, but it's being produced and it'll be out soon. I wrote a book called Cloud Native Java that's available in, so far as I know, at least 4 different languages. English, well, my English anyway. American English. What is that? That's Chinese, Russian, and then Korean, right? So I've got these 4 different books out there. Maybe there's other editions, who knows? I've got a podcast that I do. It's a podcast I do every Friday. It's called The Beautiful Podcast. It's just me talking to people in the Java and Spring ecosystems, the ambient sort of Java and Spring ecosystems, every week. Just every week, it's a discussion. I just finished the first year, so there's now a little bit more than 52 episodes out there. I do a blog every Tuesday called This Week in Spring. It's just me just me with the latest and greatest news that's fit to reprint. It's all the stuff in the Spring ecosystem that might be of interest to you. Who knows? Check it out if you like. It's also available in newsletter form as This Month in Spring. It's a digest every month, so you can find that. I've been doing that blog, by the way, for 9 years and a few weeks now. It was 9-year anniversary was earlier this month. So that's been without fail. I haven't missed a week. And this is a screencast series I do called Spring Tips, which is me at a keyboard looking at random parts of the ecosystem every Wednesday. And there's 70-odd videos of them out there right now, and I've got more coming. And I've got a book called Reactive Spring. And Reactive Spring is really what we're going to focus on today. Suffice it to say, the book is out there. It's not yet done, but you can buy it and you can start reading it right now. It's 250 pages. And as I make changes, you can, of course, feedback. And I would very much appreciate your feedback. If you buy the book now, you're entitled to the final book when it's done, for no extra cost, of course. So there's that. Now, we're going to talk about Reactive Spring today. We've only got a few hours, so let's be very, very quick and straight to the point. What does reactive programming give us that we didn't have before? Why do we care about it now when we could have cared about it 10 years ago or 20 years ago? And the answer is it gives us a way to handle more users, to accommodate more requests, handle more demand on the services that we build. So why do we care about this now? Why didn't we care about this, say, 15, 20 years ago? And the answer is fairly straightforward. The answer is that we are trying to solve this problem now because we've got increased demand. We've got increased demand, and it's not hard to figure out why or where that demand came from. It's not hard to point out where that demand sort of originated. I look at 2007 as being kind of a banner year for more demanding services or more in-demand services. Several things happened that year. First of all, we have the proliferation of mobile, right? iPhone, and then the next year Android. Suddenly came out, and suddenly everybody had a smart computer capable of running apps in their pocket. That's incredible. And then along with that came the sort of realization that we have now a world where we're no longer doing desktop-based browser experiences only, right? We have now client-service architecture. So suddenly we had multiple views on the same set of data, multiple screens that you could interact with. Each screen was talking to a back-end service. So what used to be one HTTP GET to return the HTML to render a screen for you in the browser is now, it could be a cascade of HTTP GETs calling an HTTP service of some sort, right? So you look at a screen in your iPhone or your Android application, and you might actually have a cascade of different requests that are being sent to the back end. Every little screen is now a lot more work for a given service in the back end. So this demand creates a bit of a problem. We need to address that demand. We need to be able to handle that demand, and we need to do so with the software that we've got in hand. So the question is, how do we do that? Well, there's been a fairly pragmatic answer, because what else happened in 2007? Coincidentally, I mind you, but still very, very usefully. It's contemporaneous with the proliferation and the sort of introduction of smartphones. Right around 2007, AWS, the first consumer-grade popular cloud. I'm not saying it's the first cloud. I'm just saying it's the first one that had any traction. And with that came a very interesting, very useful trick. Basically, a checkbox that you could click that says, "Hey, put this behind a load balancer," and then when I get a request, round-robin dispatch that request to the different nodes behind the load balancer. This allowed us to limp on and actually accommodate the extra demand, as long as we were willing to make some small concessions. Not so small, but still not as big as they could have been. Those concessions were that we had to move to microservices. We had to move to this architecture where we have stateless services. These stateless services excised all state from the HTTP services themselves, and they moved it to the backend data store or data tier. This is the classic Netflixian definition of a cloud-native architecture, right? In their original discussion, they're talking about Cassandra, and they're talking about HTTP-based services in the front end. Very simple idea. If you are able to do this, and it's not an easy thing to do, I guarantee you, it's quite arduous. If you're able to do this, to make this movement, to make this transition, then you're in a good place, because now you've moved all the state from the server. That means that it's cheap to scale that server up. If you want to create more instances of the service, it's fine. There's no state to replicate, so you can just create as many as you want and just do round-robin load balancing. It's a very, very useful thing to handle more capacity. Obviously, in the Netflix use case, they also needed a horizontally scalable data store, right? So they used Cassandra. That was their definition. So if you've moved to the cloud-native way, right, some microservices and so on, and you have a cloud platform, any kind of cloud platform in the last 12-odd plus years will support this basic trick of round-robin load balancing your services. If you have that, then you can handle scale. It's not super easy. I'm not saying it's the easiest thing in the whole world to do, but it allows you to scale. It allows you to handle more users. But I consider this a sort of compromise, a little bit of a concession, a half measure. You see, we can and we should do better. The question we must ask is, why can't we handle more demand with our given software, with a single node, with a single instance? Why can't one single application handle more users? Why do we hit a saturation point in our current software, requiring us to scale out and have more horizontal nodes? And the answer, for a long time, has been, and is true for the moment, that threading, the thing that we use to be able to handle things in concurrence on the JVM, is expensive. Each thread takes about 1 megabyte of context. That megabyte of context is bookkeeping that the operating system has to do to manage the native operating system thread. So if you have 1,000 threads, you've already wasted a gig of RAM, and you haven't done anything yet. But let's say you had 1,000 threads. Could you actually do 1,000 things at the same time? Let's say you were willing to accept the cost of spinning up 1,000 threads. Could you do 1,000 things at the same time? Usefully? Probably not, right? Remember, threading by definition is just an illusion. Beyond the number of cores on your machine, you don't actually have 1,000 concurrent things, right? You have whatever number of cores you have. That's the best you're going to ever do in terms of true parallelism. So, you've got 1,000 threads. What happens? Well, each of these threads is vying for time on the CPU. So you get thrashing, right? You get resource contention. So paradoxically, by adding more threads, you've now made it so that there's a queue for each thing to get time on the processor, and each thread has to ask for a spot on the processor. And so each one of them has that queue. It actually takes longer to handle any more requests, and you don't handle more requests, right? So each request is slower, and you're not able to handle any more work than you would have if you just had created enough threads to match the number of cores. So creating too many threads is not a good idea, right? And this is one of those things you quickly discover after you've had to debug a web server issue somewhere. So that's why we have to scale out. That's one of the reasons that we have to scale out. The question is, why though? Why can't we do something to make our code be a little bit more responsible with the resources it's been given? Threads are getting cheaper in the JVM. In a few years, hopefully, knock on wood, they'll be much cheaper, right? Thanks to the fibers, this idea of fibers, or lightweight threads, I guess they're calling them now, that are going to be introduced in the JVM. So that'll solve one problem, hopefully. It'll make it a lot cheaper to create threads. But we still don't have a good answer for how do we design systems that are inherently distributed and inherently volatile. We don't have a programming model that allows us to say, hey, this thing I'm doing over the network may fail, right? We don't have a way of dealing with that naturally. Right now, all of our code assumes that the internet is infinitely fast, there is zero latency, that the services and networks are always available, and so on. And this is a lie on which we cannot afford to predicate our system. So we need to do a little bit better there as well. We need answers to both these things. How can we make better use of the threads that we've got? And then how can we write code that does the right thing in the face of volatility, in the face of distribution? So this is where reactive programming comes in. Reactive programming is a programming model that gives you a better way of reusing threads that you've got. In order for it to work, though, you have to rewrite the way you think about input and output. Or really, actually, you have to rewrite the way you think about anything that could end up monopolizing time on the CPU. So what takes time on the CPU? Well, computationally inefficient things, right? Slack, for example, takes lots of time on the CPU. Super expensive, not a great idea. Fibonacci series, right? It's a very classic algorithm. The Fibonacci series takes a lot of time on the CPU. Cryptography, Bitcoin mining, these kinds of things, right? Password encoding, these all take time on the CPU. There's nothing you can do to make that go away either. You can't rub reactive on this and suddenly it's fixed. It's still going to take time on the CPU. That's the very nature of those kinds of algorithms. Fair enough, okay? We grant that those have to use time on the CPU, and therefore they are perfectly appropriate for a perfectly appropriate use case for threads. But what about input and output? Does that need to take time on the CPU? No. Our operating systems have a way of monitoring file descriptors and then giving us a callback when there's activity on that file descriptor. The only reason it takes time on the CPU right now is because in order to do input and output, we sit on a thread using traditional Java I/O input and output streams. In order to do that work, we have to sit there and act and wait for bytes to arrive. And when we're waiting, what are we doing? We're sitting there parked on the thread, waiting for the next byte to come down the wire. That's the reason we're sitting there on the CPU. We're wasting a slot on the CPU, but we're not doing anything with it. And this is really unfortunate because if you look at most modern software today, you realize that they're very idle. We can't create more threads, we can't do anything more, and yet if you look at the actual activity, nothing's happening. They're all just parked waiting for the next byte to arrive. This is a problem. This means we're not being very efficient with our software. So reactive programming also gives us a way to reclaim some of that lost space. It's a much better bin packer in terms of computations. Okay? So reactive programming gives us a way to say, hey, instead of synchronously sitting there and waiting for the next byte to arrive, instead I'm going to ask for the data, and then I'm going to jump off of the CPU. And when the operating system, I'm going to tell the operating system, here's a file descriptor, watch it for me, and when there's data, give me an interrupter, give me a callback, and I can use that to then start processing. That's very, very useful. That callback is a little bit hard to work with, though. It means that we have to change the way we write code. It's now asynchronous. We're now dealing with data as it arrives instead of when we want it to arrive. That's fair, right? So we need to rework the way we write this code. Of course, you can see that there's an implied change in the way we write code here. That's not going to be great. We're not going to enjoy that. But if you're willing to do that, if you're willing to take that step. So if you're willing to do that, then we can do some very interesting things today. So that's what we're going to talk about, my friends, is we're going to talk about writing software that takes advantage of this new inverted style, where instead of saying, here's my data, and I want to pull the data out one byte at a time, instead of doing that, I'm going to ask for the data and have the data pushed to me asynchronously out of band whenever it's available. That inverted way of dealing with data is a little confusing at first, but it gives us a much more useful way to build software. That's what we're going to talk about. The question then is, how do we describe this kind of asynchronous inverted kind of data? We need some kind of computational metaphor that allows us to work with data of this type. And so we need some common abstraction that can be used to model this data, to hold this data, to work with this kind of data in our software. So a number of different organizations several years ago got together and we converged and extracted out a common ground set of interfaces called the Reactive Streams Specification. These are 4 very, very simple interfaces that are the work of, or the product of Pivotal, VMware, that's where I work, is VMware, the product of Netflix, Lightbend, nay TypeSafe, and the product of the Eclipse Foundation. So all these different organizations got together and we extracted out these 4 very simple interfaces. They represent a way of describing asynchronous streams of data. These are the foundations for processing solutions that sit atop those 4 very, very simple types. That's where Project Reactor comes in. Project Reactor plugs the holes in that very, very simple API, and that very, very simple type system. It gives us an API for processing streams of data, not just for describing it and holding it, but for actually doing computations on it, for plugging in the common used operators like map and flat map and filter and so on. Project Reactor is one of many such alternative options. You also have RxJava from Netflix. You've also got Akka Streams from Lightbend. You've also got Vertex from the Eclipse Foundation. So all these different things support these reactive streams types, so they're interchangeable. Now, all those things that I just mentioned are very useful in and of themselves, but they're not really a solution that I would go to production with today, not by themselves. You see, they don't answer the question of, hey, how do I actually build workable software today? How do I handle the daily bread and butter tasks that I have to deal with in getting software into production for my business? How do I do web services and data access and security and all these kinds of things and microservices? What do I use to do that? So then we have things like Spring. Spring Framework 5 shipped in 2017, so getting close to 3 years now. Spring Framework 5 shipped a brand new reactive web runtime built on top of Project Reactor, which in turn builds on top of the Reactive Stream specification. Spring Framework 5 is the foundational layer, on top of which we have since released new versions, new reactive supporting versions of Spring Boot, Spring Data, Spring Security, Spring Cloud, etc., etc., etc. So that, my friends, is the journey that we're going to walk today. We're going to see how all these things plug together to allow you to build reactive services and software. And we're going to do so, of course, my friends, we're going to do so by going to my second favorite place on the internet. Obviously, my first favorite place on the internet is production. I love production. You should love production. You should go as early and often as possible. Bring the kids, bring the family. The weather's amazing. It's the happiest place on earth. It is better than Disneyland. But if you have not been to production, you can begin your journey here at start.spring.io. If you need inspiration in the early morning before a cup of tea or coffee, start.spring.io. If your children are restless and they cannot sleep, start.spring.io. And if you suffer from indigestion after a long night of alcohol abuse and PHP, start.spring.io. So we're going to build a new application, friends. We're going to build a new application taking advantage of some of the options and some of the features on start.spring.io. First of all, there's a dark mode. I think that's awesome. Second of all, we can choose a Maven or Gradle project. That's fine. Java, Groovy, or Kotlin, all of which are great. I'm going to name my service the reservation-service, and I'm going to specify a few options, a few things that we really do need to address before we can move forward, some of which may be confusing for you if you've not yet seen these options. So let's do our level-headed best here now to explain when and where to choose which. If you come down just a little bit, you'll see 2 different selections here, 2 different things that you need to consider. The first of which is the packaging that you would like to use for your application. People are often confused by this. They don't know when and where to choose which option. So I'll do my best to explain. If by some fluke of physics, some terrible, terrible tragedy of time and space, you find yourself somehow trapped in the distant, distant, distant past, then choose .war. But if you're here with me in 2020, then choose .jar. This is a big part of my overarching and guiding personal philosophy of make jar, not war. And again, lots of options. Lots of things you could do, but I encourage you to accept the defaults. Very good. Now, my friends, we also are confronted with the choice of Java. What version of the JVM would you like to use today in 2020? Before you, my friends, you see 3 different options, of which only 2 are valid. I don't want to give away the surprise about which one is the wrong one, but I'll give you a clue. When you discover it, when you figure it out, don't tell anybody else, okay? Save the surprise for them. I'm going to give you a little clue. Shh, okay? Did you get it? Okay. So that's the wrong one to use. Java 8 is no longer the acceptable version of Java to use. It's completely wrong in every context. I would never use that. Not on purpose, not even by accident, not even in my worst drunken bender would I accidentally deploy Java 8. You need to be off of Java 8. Do it for yourself. Do it because it's technically inferior. Java 11 is the current long-term supported version of Java. It has a longer shelf life. It has a lot of great features, great syntax. It's mature. It's got a lot of performance enhancements, new security improvements. It's an incredibly good version of the JVM. And I would use that if you were a coward. If you're a coward and you feel that you don't have the chops to maintain Java, which is, who says that, right? It's just Java. You just drop it in and it upgrades easily. If you're a coward and you can't maintain a new version of Java every 6 months, then stick with Java 11. That's fine. It's not great, but it's fine. If you're on a cloud platform, they're going to treadmill you to the next version of Java anyway. You might as well just use the latest and greatest, right? Make it your platform's expense. So use Java 11 if you're a coward. But if you want to do the right thing, then I would recommend Java 13. Java 13 is awesome. In fact, it's almost obsolete. Java 14 is now in ramp down phase, so that'll be out soon. New stuff like records are already available. You can try them out. So Java 13 is what I'm going to use. Java 13 and Java 11 are both technically superior than Java 8. They have tons of new features that make them eminently more desirable than Java 8. They're also morally superior to Java 8. They're morally superior to Java 8. Are you prepared for that discussion? Are you prepared to go home and have that discussion with your children and tell them you're still using Java 8 in production? I don't think you are, friends. I don't think you are. Have you ever seen Heartbreak? That's that discussion. Don't do it for me. Do it for the children. Now, my friends, we're going to bring in some of the dependencies that we want. We're going to bring in the reactive web support. So we're going to bring in Spring's reactive web support. We're going to bring in Lombok, which is a compile time annotation processor that makes Java just a little bit less painful. We're going to use reactive MongoDB here. We're going to use R2DBC and Postgres. I know they compete, but we'll use them both. We're going to use RSocket. And I think that satisfies my basic desires for this single application. So reactive web, Lombok, reactive MongoDB, R2DBC, and RSocket. I'm going to hit generate, and that's going to give me a zip file that I'm going to then open up in my IDE. So here we are, downloads. Okay. Alrighty. Okay, there it is. I'm going to open this. I've got a little zip file. I've got a little program called unzip and open. It's just a little Python program that goes to the zip file and unzips it and then runs idea space pom.xml. You could actually just originate this project in your IDE. You don't actually have to start them from start.spring.io. There's a wizard in your IDE, be it NetBeans or Eclipse or IntelliJ. That wizard uses start.spring.io behind the scenes. So it's not like you're going to get inconsistencies there in the generation. It's the same API, same process, etc. All right, so I have a brand new project. Oh, that's good water. I have a brand new project. Can you see this font? No, you can't. I'm not even going to. Let's see, font. How's that in the back? What about in the distant back? Bigger, yeah. 30. In the back, who cannot see that? Raise your hand if you're having trouble. I'll happily make it bigger, no problem at all. Okay, 34. Can you see that in the back? Okay? Woo, that's big, look at that. Okay, we're going to try. I've never done it that crazy. All right, so we're going to build an application that writes data to the database. In this case, I use that term sparingly, charitably. I've got MongoDB here. Let's comment out R2DBC for the second. Comment out the R2DBC dependency. and I'm going to create an object that's going to map to a record in MongoDB. Now, in MongoDB, you have this idea of a collection. A collection is a thing that has multiple records inside of it, each one of which is called a document. So I'm going to annotate this object with @document. I'm going to say that it has a string ID and a string name. Okay, so there we go. Now, the ID is the key. Okay, now that's the essence of what I want to express. It's an object that has a getter, it has an ID and a name. But of course, this is Java, so I have to create some getters and setters and toString and hash code and equals and all this good stuff, right? Good clean Java code in 2020 is actually pretty terrible. So we're going to go ahead and get rid of all of that, and I'm going to use Lombok. Lombok's a compile time annotation processor that allows me to then make short work of tedious, soul-annihilatingly boring things like that. Okay, so there's my annotations. These are compile time annotations. At runtime, it'll be as though I had typed out public string get name and public void set name string, etc. Okay. Now I want to manage instances of this data. I want to talk to the database. To handle that, you use a repository. A repository is a design pattern. It is a thing that's meant to insulate your higher level business logic from the tedious, soul-annihilatingly boring reading, writing, updating, and deleting logic at the lower level. So we're going to create a reservation repository. Now this is just an interface. You don't have to actually implement it. Spring will do that work for you. So we're going to say implement this. And there we go. There's my basic interface. This interface has a bunch of methods whose names should be fairly straightforward, I expect. Save, save all, find by ID, check if it exists, count, delete, etc. All these things are fairly straightforward. What may be a little strange for you, for those who haven't seen it yet, are the types. The first of which is a publisher. A publisher comes from the Reactive Stream specification. It is a thing that, it publishes. That's the whole point. It publishes data out of band to a subscriber. The subscriber consumes that data asynchronously as each record becomes available. So when the subscriber first subscribes, the onSubscribe method is called, and the subscriber is given a subscription. As each new record arrives, be it 1 byte or a customer record or a long or a date or a string or an order object or whatever you want, right? It can be anything. As each one of those new records arrives, the onNext method is called, with each element being passed in as a parameter. So you might get called one time, you might get called a trillion times, or you may never stop being called. There's nothing in the spec that determines that upper bound, right? The onError method gets called when there are errors. Okay, so the errors get propagated through this callback method, and that's very natural because remember what we're trying to do is to move the flow of execution from one thread to another very naturally. So we don't want to take advantage of try-catch because we have no idea on what thread that might have occurred. Instead, we propagate errors through this very functional sort of mechanism. We treat it as just another kind of data. You've got records of type T, and you've got errors, okay? So they get propagated through here. When we're done processing the data without any errors, then the onComplete method gets called. Now, I briefly explained subscription here, but let's double click on that and kind of see what that gives us. Subscription is a lot more important than it seems. A subscription is a thing that each subscriber is given. Each subscriber gets a reference to the subscription, and they can use it to request more data of the publisher. They do that by calling request. So the subscriber, the client, the consumer, the thing that's actually processing the data, drives the rate of consumption. This is super important. This is flow control. If you've ever built any kind of basic networking, if you've ever had to do any kind of basic TCP/IP programming or programming, you have to think about what happens when one side of the equation goes faster than the other. It's flow control. It's fundamental to everything we do in distributed systems. Here, we've surfaced that very simple idea as a part of the top level of the API. Now you can exert control over flow control. In the world of reactive programming, where sometimes marketing prevails over common sense, this very simple idea called flow control, which we've had to contend with ever since there was one computer on the same network as another in the history of computers, that very simple idea has been rebranded as back pressure. So if you hear the term back pressure, it just means that the thing that's dealing with the data has the right to push back on that data, to say, I don't want any more data. So the consumer can request one record and then request nothing more. Or it can keep requesting data, right? And if it requested 10 records, there's no guarantees about anything beyond that it's going to get 10 records. It may get 10 records in the next 10 years, or it may get 10 records in the next 10 nanoseconds. You don't know. That's the whole point, right? It's asynchronous. But you're not going to get more than 10 records. So you want to size that number to be something that you could accommodate and you could handle processing if it all arrived in your lap at one time. So hopefully it's not going to be like, you shouldn't put like 1 trillion records because you're not going to be able to do something with 1 trillion records, right? If you want to cancel the production of data, you can call, guess what? cancel. So we've got now publisher, subscriber, and subscription. There's a fourth type. I did say that there's a fourth type, and that's called processor. Processor is a different package. Processor is a interface. It's a bridge. It's a source and a sink, a producer and a consumer, a publisher and a subscriber. And that's it. That's the entire reactive stream specification. If you understand that, congratulations. You're ready. Go to Silicon Valley, raise $1 million, blow it all in stupid parties and come back a failure. You're already years ahead of most people in the Valley. You can do this. Now, these basic types form a foundational layer. I trust you can see that they're very Spartan, simple interfaces, but they're very useful. They're foundational. And so they're so useful, in fact, that they've now been incorporated into Java 9, which, again, is 2 years old, right? So Java 9, it's more than 2 years old. It has it in Java util concurrent flow, which is the top-level type, dot processor, dot subscription, dot subscriber, and dot publisher. So when you use reactive APIs, it's perfectly reasonable to pass around either the JDK 9 variant or the reactive streams variant. The reactive streams variants tend to work on Java 8 code bases. But again, you shouldn't be using Java 8. So what do you care? It's moot for you, obviously. Now, we have these very simple types, but I did say that they lack some of the flexibility, some of the operators, some of the things that we can use to actually process streams of data. That comes from Project Reactor, among other things. And Reactor gives us two specializations, the first of which is a mono. Now, a mono is not, if you speak Spanish, a monkey. It's a thing that produces at most one value. It's like a completable future that supports back pressure, okay? It has a bunch of operators, though, lots and lots and lots and lots of operators, right? 1,250 lines of code that you don't want to write with that very simple interface. So that's very useful. It's a publisher that produces 0 or 1 value. There's also Flux. A Flux is a publisher that produces 0 to n values, where n could be unbounded. It could be 0, it could be 2, it could be a trillion, it could be infinite. Okay? But again, lots and lots and lots and lots and lots and lots and lots, lots and lots and lots and lots of operators. 2,227 lines of code there. Again, very simple interface, but it's surprisingly hard to get this right, so don't write that code yourself. This is not the kind of code you want to cut your teeth on. You're just going to waste a year doing it, and you're going to get it wrong, right? Due respect to you, of course. I'm sure you're gifted, but you're going to get it wrong. Just trust me. So we have this very, very simple interface, but it gives us a lot of opportunities to now write reactive data access logic. So let's do that. I'm going to create a sample data initializer. I'm going to write some sample data to the database, creating an application ready event like so, public void ready. And I'm going to inject here a component. I'm going to make this a component. It's a Spring Bean that Spring will see when the application starts up. And it's going to call that callback interface and give me a chance to initialize my state. I'm going to use that to write some sample data into the database, which in this case is my MongoDB instance running my local machine in the background there. Okay, so I'm going to create a publisher of names. Let's go think about some names here. We've got Stefan, right? Okay, that's a name on the Spring team. We've got Madura, another name on the Spring team. I'm Josh, nice to meet you. I'm on the Spring team. We've got Ria, she's awesome as well. She's on the Spring team. We've got Dr. Sire, he's awesome as well. Got him on the Spring team. We've got Violetta, and we've got Glenn, of course, and we've got Cornelia, she's awesome as well. So there we go, there's a few names, right? Actually, you know what? We can do Bella Yushin. There you go. There we go. She's awesome as well. There's a bunch of names on the Spring team. Now, what I'm going to do is I'm going to turn that into a list of names, okay? Names. And I'm going to visit each one of those names and write it to the database. I'm going to say new reservation, passing in null, and that gives me a stream of reservations, okay? Now I want to turn each one of these into a record that I save into the database. I'm going to call flat map like this, passing in R. There we are. So there's my saved records. Now, what I did is I called flat map, and the reason I called flat map is because when I called .save, save returns a mono, a reactive type. It's a publisher. And so what I would actually have, if I called map, I would have a publisher of publishers, right? It would be, let's see here. It would be two publishers, one within the other. So a flux of mono of reservation. I don't want those two publishers. I want to unpack it. I want to flatten it, if you will. So that's why we say flat map, okay? Flat map unpacks the inner publisher and gives you just one publisher so you can more readily deal with it. So there's my data. It's been saved in the database. The problem, of course, is that if I run this code, nothing is going to happen. And the reason nothing's going to happen is because you have to actually activate the pipeline. You do that by subscribing. And there's a lot of different overloads here. You can actually write out, for example, each record. You can have a callback there to log out each record as they arrive, turn this into a method reference, and there you are. That's a very simple thing to do, but think about what's going to happen if I run this program multiple times. The first time I'll run it, I'll have 8 records in the database. Second time, 16. The third time, 24, etc., etc., etc. I don't want duplicative data in the database. So what I want to do is I actually want to delete everything. So I'm going to say reservation repository dot delete all. And notice that that too returns a reactive type, a mono, a void. So then I'm going to say asynchronously, then after all that's done, I want to then save the data that's in that pipeline. And then finally, I'm going to find the data. Okay? And then finally, as all of that is returning, I just want to log it all out, just as I did before. Okay? So that's a pipeline. I've actually got a happens before quality to this, right? I'm actually saying that step 1, delete everything, happens before all the things in the save pipeline, and all of that happens before the finding of all the records, and all of that as each record is coming back, as they start to trickle back, I then log it out. Okay. Now clean this code up a little bit here. var is much nicer, of course. You can do that because it's 2020. So here we go, and get rid of that. Chain these things together. There you go. So that's my new pipeline cleaner. Okay. So there we go. I've got a pipeline. I'm going to delete everything, save the data, find the data, and then print it out. Okay. Let's see what happens if this works. Did it work? Looks like it worked. There we are, we happy few. There we are, all 8 of us on the console. You can see that it's round trip to the database. It got a UUID for each ID. It wrote the name out, so it seems to have worked. Everything's fine. That's good. Of course that worked. It was a demo. That was always going to work. That's not what I wanted to talk to you about. What I wanted to talk to you about, as always, is this. This is the Spring Boot ASCII artwork. Now, this artwork took a long time to get right, but we on the Spring team have many people who are PhDs, people who in their previous lives worked in nuclear physics, star stuff. The very celestial bodies in the heavens above us were their daily bread and butter. And so it's for this reason that I want to take a very brief digression to talk about what I consider to be a serious and glaring deficiency in the IntelliJ JetBrains product. For while I'm a fan, I consider this to be particularly short-sighted. Do you see that checkbox right there? That one right there. Do you see that checkbox? This one right here. Do you see it? Do you see that checkbox? That one right there? This one. Do you see this checkbox? That checkbox, once clicked, don't click it. Once clicked, that checkbox suppresses the output of the ASCII artwork. What the hell? Why is that there? That's a dumb feature. Nobody even asked for that feature. So I did what all people would have done in the same situation. I went on the internet and I cried, and I was given a message of hope from my friend Jan Sabron. Jan Sabron is a developer advocate at JetBrains. This is Jan right here. This is him. That's him. Boop. Anyway, he sent me this message of hope, which I want to share with you here today. He's a friend. I've known him for years and years, and I want to believe him when he says it's going to be fixed. I want to believe him, but you know what? I'm starting to think that just maybe, he's not exactly on the level. Again, not sure what it is about him, but I'm just starting to feel like he's not telling me the straight dope, so I'm not sure. Whatever. Anyway, I've got now data in the database. I've got amazing ASCII artwork. I've got data in MongoDB. I like MongoDB, but that's not the only thing. We've got a number of different reactive data options. You can do reactive Cassandra. Actually, better yet, there's as they say, there's always a tweet for that. So, okay. Here we are. Here are the NoSQL options here. So we've got Microsoft Azure Cosmos DB, Google Cloud Firestore, and Google Cloud Spanner. We have Cassandra, MongoDB, Redis, Neo4j, Couchbase, and Elasticsearch. All support reactive NoSQL persistence. Okay, so there's a lot of different options out there that have reactive options. So you can use the non-reactive option, which is you may you may well already be using those. But there are separate code bases, separate projects that usually have the word reactive in them. So you'll see there's Spring Data Reactive MongoDB versus Spring Data MongoDB. These are built from the ground up on an asynchronous I/O driver. They're completely different code bases built on top of totally different implementations, but you can use them, and they're mostly feature complete at this point. In fact, there are some things that are better expressed and better done in the Reactive API, in the Reactive style. Now the question then, of course, is, sure, I like that, obviously, but is there anything I can do to talk to a SQL data store? I've mentioned a bunch of SQL data stores, and I've mentioned a bunch of NoSQL data stores. How do I talk to a SQL data store? And this isn't something that was well served, so we created something to solve that problem. It's called R2DBC. R2DBC is a reactive relational database connectivity abstraction, hence the R2, right? R2DBC, reactive relational database connectivity, and it's a core SPI that it's sort of like it's akin to JDBC, but it's reactive and it supports these reactive streams types. And we even went ahead and built the implementations for a number of different databases, including PostgreSQL, H2, and Microsoft SQL Server. Now, other database vendors have come along and implemented their own as well. So there's more coming. There's SAP HANA, I think, has one coming. I think some people are working on an Oracle one. I'm not sure who that is or what, but there's that. There's a MySQL one as well. So there's a lot of different options out there, okay? And more coming all the time. So you can use R2DBC with Spring. Now, R2DBC itself is now GA, and the Spring Data R2DBC project is GA. But the auto configuration, literally 2 or 3 classes, that auto configuration that makes R2DBC work with Spring Boot isn't yet in the GA version of Spring Boot. So what I had to do when I went to the start.spring.io, I checked R2DBC, and Spring Boot gave me the experimental, scary experimental jar. But really, it's a very thin layer on top of what is actually GA code. So I'm going to go ahead and comment out MongoDB. Goodbye. And everything else, I'm going to leave as is, except for this. I'm going to restore the R2DBC Postgres implementation. Okay, there's this. Some things are a little bit different. In MongoDB, my document ID is a string. It's a UUID. But in my monotonically incrementing primary key scenario with my SQL data store, I have an integer. So I'm going to change that. I'm going to change that here as well. And then otherwise, it's basically the same thing, right? So I can now run this code, stop and rerun. It's saying I need to provide a URL, which is very, very prescient. So we go here to application.properties, r2dbc.url, r2dbc:PostgreSQL, localhost orders, and of course, username, orders, and password will be orders. Okay, so there we go. Having done all that hard work. Don't tell anybody the secret password, okay? There we go. So now it's gone to the database. You can see it's created the records. It's written them to the database. Primary key. And actually, I can confirm as much. PC equal u orders. Orders, select all from reservation. And there we are. Right? There are the records that we wrote in that simple interaction. Now, let's suppose, sorry? Was there a question? Okay. Question? I could have sworn I heard something. Sorry, okay, good. So let's suppose that you wanted to manage all this data and you wanted to do so in an atomic way, right? Very simple use case. Suppose you wanted to do transactions. This is a very common question. How do I handle transactions in the world where the flow of execution can very easily and usually jump from one thread to another? This is a very common thing, and there's a very easy answer to this. Think about the way transaction demarcation typically works in Spring and in other frameworks. You've got storage associated with each transaction that lives somewhere that all the framework code can then find it. That storage is usually a thread local. That is to say, you've got something that is keyed to the current thread. It's alive and it lives along with the current thread. And so as long as your database transaction logic happens in the same thread, then it works just fine, right? Somebody installs the thread local up there, starts a transaction, and then when you're done doing whatever business logic you want to do, something, an aspect in Spring or whatever, comes along and then commits the transaction by looking at the current thread local and grabbing the current transaction. Works great in the old non-reactive world. But what about in the reactive world? How do we what gives? How do we do that same thing in this brave new reactive world? So in order to support this, we had to create something called a context object. So you can see that this pipeline actually has, I can actually provide a context as well, and I can provide arbitrary keys and values, or new, it can be anything. It's just an object for the value, right? So I can provide a context. That context is like a map. It's a dictionary of values that will be associated with the current pipeline. So it doesn't matter on what threads this pipeline executes. It doesn't matter if this executes on one thread and this on another and this on another. It'll make sure that the storage lives along with the pipeline, that it's propagated along with that pipeline. So we have now reactive transaction demarcation, and it just works automatically. So I'm going to create a very simple service to demonstrate this. Let's create a service called a reservation-service. And the service is going to then, what is it going to do? It's going to create a bunch of reservations, but it's going to do validation. So if any of the names that it's given are not valid, then it'll abort. It'll roll back the transaction and fail the entire thing. It won't write any of them. So either it'll write all of them or none of them, but nothing in between, right? You don't want an inconsistent state. So I'm going to inject my reservation repository. Okay, and I'm going to make this a required args constructor. And there we are. There's the required args constructor. There's my reservation repository. What I'm going to do is I'm going to say, for each of these names, flux.from array names, from each one of those names, turn this into a new reservation. Okay, passing in that. And then for each one of those, I'm going to save it to the database just like we did before. And I'm going to then do some validation. So I'm going to say, on each new reservation, assert that the name is valid. Okay, so private boolean is valid. Reservation R. And what I'm going to do is I'm going to say var r name equals r.getName, rname.car at 0, var first car, and I'm going to say return first car is uppercase. Okay, so the name must start with a valid uppercase character. So I'm going to say is valid, passing in R. And if it's not valid, then I'll return a message. So it'll say the name must start with an uppercase. All right. So there's my entire reactive pipeline. Now, I can clean that up a little bit. Use a method reference. Very good. And there's my basic pipeline. Now, in order for this to work, I need to enable transaction demarcation. And the way you do that is, first of all, you have two options. You can say @enable transaction management, and this looks very similar to what we had before, except that instead of using the platform transaction manager abstraction, you're now using the reactive transaction manager abstraction. Okay, and so we have reactive transaction manager implementations for a number of different reactive data stores. We have R2DBC, which is what I'm using here. We have MongoDB. We have Neo4j, etc. Right? There's other ones as well. So here's a reactive transaction manager, and that would do it right there. That would be enough to get you started in this way. You could actually then decorate each method and say, hey, this is transactional, like that. Or you could be explicit. You can use something called a transactional operator. So transactional operator, like that, and you then isolate the whole graph. You say this dot transactional operator dot transactional, and then put that in there. Okay. So there's the pipeline. I'm actually wrapping individual parts of the graph. This is more like the transaction template with which you might be familiar if you've ever used the lower level transaction management facilities in Spring. So transactional operator is a very simple thing, but you do have to create it. So you have to inject the reactive transaction manager. RTM finally means something else than what we are used to. Okay, there we go. So now let's see that in action. I'm going to, instead of doing the pipeline down here manually, I'm going to use our newly minted service. So reservation-service, reservation service, and I'll keep the names. Whoop. Dot save all, and there we go. Okay. So gesund. So there's my pipeline. Let's see what happens. Okay. So right now it should work. Let's just run the same code just to see that everything's working. That should be the happy path. Then we'll go back and lowercase a character to see what happens. All right, that seems to have worked. Great. Madura, lowercase r, m. It's going to log out the exception, of course. There we go. But now, there's nothing in there. So you can see it deleted everything, because remember, that happened outside of the pipeline, outside the transaction. Then the pipeline where we save the data here, that's in the transaction. So that's atomic. It's either all or nothing. And then we find the data. Well, it deleted everything. And then it didn't write anything to the database, even though only one record had a lowercase character. So it atomically rolled back the transaction just as you'd expect. It's really nice to me that in 2020 I can do a talk about transactions and SQL data stores and have it be exciting. Thanks, Reactive. So, all right, now we have data in the database. We have reactive transaction demarcation. We've looked at NoSQL and SQL in the reactive world. You can see there's really nothing to it. It's fairly straightforward if you've ever used Spring Data. Now, what about building an HTTP service? I'm going to want an HTTP service. So one thing I can do is use a Spring controller, a REST controller, a very natural thing to do. But I much prefer the functional reactive router function style. So routes, return, route, build, get /reservations, new handler function, new server response.ok.body. Okay? And I'm going to inject here my reservation repository. So rr.findAll.class. All right. So there's this. Okay, so that's my new functional reactive endpoint. That one, imagine a class. I would have a class reservation REST controller, and then get mapping, and then public collection or public flux of reservation, get all reservations, and then return reservation repository dot whatever, or just this one line, right? It's a very, very concise way of saying, hey, here's the predicate. It's an HTTP GET. It's a URL for /reservations. And when that request comes in, invoke this lambda, which takes the current request. That's this variable that I just kind of ignored here, and return the OK HTTP status 200, and then return a body with the data from the database by calling the reservation repository. Okay, so let's see what that looks like. I quite like the style. It grows on me. You can do all sorts of other things. You can do all the content types. You can do all sorts of other things there. Very useful. Let's see what I did wrong. Oh, my hoisted by my own petard. Let me see. Here we go. Good thing I got that validation. Okay, that worked. So now, reservations, there we are. Okay, there's my simple HTTP service. It's a functional reactive endpoint. And remember, this is a builder, right? It's a builder, so I can actually go here and chain these together. I can create as many as I want. I can do for loops and if then, so I can conditionally register HTTP endpoints based on some whatever, any kind of criteria or predicate I want. So okay, we've got now HTTP, we've got data in the database, we've got JSON. So what? Who cares? Like, it's 8 records. You could have done 8 records yesterday, right? You could have done that with JDBC and the servlet API. You don't need me for that. You don't need reactive for that. Where reactive programming really comes into its own is not just in achieving parity, and I would say that I've demonstrated that you have parity, right? This is not more complicated than anything you've done before, and you're getting better performance, but you're still just doing the things that you could have done before. Where reactive programming really comes into its own is when you start taking advantage of opportunities to do things that would have otherwise monopolized threads. So think about things that monopolize threads. What use cases monopolize threads? Well, suppose you want to do something that is lively, right? You've got a feed like stock ticker updates. That's a very lively thing. You want fast responses. You want immediacy. You want liveliness to the data. So it's much better to have a socket that stays connected. In the old world, a socket equals a thread. So you can only create as many sockets as you have threads. You're limited there. Well, in the reactive world, that's not the case at all. You can have a good deal, many more file descriptors or sockets or whatever open than you can threads. And the reactive world makes that work. It makes it okay. So another thing that you could do with lively data, what's another example? Chats, right? The common chat scenario. Anything with a live feed of data is a very natural candidate for this. So let's create a service, an arbitrary little service here, that returns an infinite stream of results. Greetings service. And it's going to be a simple service that's going to, when prompted, return a stream of greetings responses, like this, given a prompt of type greetings request, like this. So private string name, okay? At data, at all_args constructor, at no_args constructor. Okay, paste that in there. Put that in here. Good stuff. So now, I've got a request and a response, and I'm going to create a service that produces an infinite stream of greetings responses. Okay, so greetings request, and I'm going to return a infinite stream like this, an infinite reactive stream. So return a new greetings response, hello, request.getName at instant.now. Okay, so it's an infinite stream. Now, this is an infinite stream, and that's fine, but I want to stagger the results. So I'm going to delay the elements. I'm going to say, okay, create a new stream of records every second. I want to create a new response that gets sent back to the client. Let me put it all in one line here. It's a little hard to read either way, it seems like. Okay, so there we go. So there's the infinite stream. It's going to say, create a new stream of data, producing a new greetings that says hello, name, at, and then it shows the time. And I'm going to stagger the results every second. And the reason I can do that is because there's a scheduler that's in play here. You may not realize it. You may not see it. Thus far, we've gotten all this way, and we've never had to deal with it. But behind the scenes, the thing that moves the flow of execution from one thread to another is a scheduler. That scheduler is part clock, and it's also part thread pool. Okay, and does both things. That scheduler is invisible to us most of the time. You don't have to worry about it. But it's here, and you can actually override it if you want. So suppose I went down to this line down here. Let's say that I wanted this little pipeline to schedule its work on a custom scheduler, right? I could say, hey, I want to run everything on the current calling client thread. I could say schedulers.immediate. Or I could say, create a scheduler from an executor service or an executor, right? So like that, I could create my own custom scheduler. Let's suppose that I wanted to do a scheduler like bounded elastic, or sorry, unbounded, right? Let's see, elastic, there you go. So elastic is going to create a new thread every time a thread is needed. This is not exactly what you want. By default, the scheduler that you have in play will create one thread per core. Well, what we're doing here is we're just creating more threads as needed all the time. So this isn't going to be great. It's something you might do if you were using blocking code. So the question then becomes, how do you discover where you have blocking code? Right? You don't want to run blocking code on this very finite thread pool. The default scheduler gives you one thread per core. So you've got 4 cores in your machine, you've got 4 threads. And that should be enough, as long as nobody stays on the thread for too long. As long as all you do is kick off the pipeline and then jump off the thread so that somebody else can do the work, or do more work, or launch more work. So if you want to find that blocking code, you could do some very, very tricky debugging, or you could take advantage of something that we created for you called Blockhound. Blockhound is a Java agent that you can add to your code base. You just add it to the class path, very simple. You do blockhound.install like this right here, and then do something that blocks the thread, like thread.sleep anywhere in the code. And it'll throw an exception, blocking operation error, blocking call, right? So that Java, isn't that cool? Yeah. It's awesome. And we wrote it to be generic. So we built a plugin that supports Reactor and ArcsJava. I think there's even a proof of concept that shows akka streams. And if you've got some other thing that you want to be able to catch blocking API calls in, then you can adapt it to that SPI, and you can teach it to do that as well. Okay. So this is very good for isolating these blocking calls. So my point is, you shouldn't need to control the thread pool unless you're doing something that's blocking. And you might just be doing that by accident. And so if that's the case, use Blockhound to ferret it out and then get rid of it and then go back to not having to worry about the scheduler. But that scheduler is there, and it gives you the ability to control time, right? You can think about time as a dimension of your API. That's why I can do something like that, where I delay the elements, okay? Now, I've got this never-ending stream of data. I want to convey that to you. I want to demonstrate that to you in action. So what I'm going to do is I'm going to create a WebSocket endpoint. I'm going to create a simple WebSocket endpoint here. I'm going to say greeting WebSocket configuration. Okay, I'm going to create 3 beans, a simple URL handler mapping. Now, WebSockets are a binary protocol that connects to it upgrades to it's an HTTP, it's a protocol that you access via HTTP that then gets upgraded to the binary protocol. So the client connects to some HTTP URL, in this case, ws/greetings, and then it upgrades, it does a handshake and it upgrades to the WebSocket protocol. So what I'm doing here is I'm telling the container, Spring, hey, I've got this HTTP URL, I want you to map that to my WebSocket handler, okay? And the WebSocket handler, we haven't yet built, but we're gonna do that in a second here. So I'm gonna inject that reference there, and I'm gonna give it a URL order. So I'm gonna make sure that's the 10th priority in the framework, okay? Now, we've got the handler mapping. We need to create a WebSocket handler adapter. That's just infrastructure code, and frankly, I don't know why I have to write it, but I do. And bean WebSocket handler, okay? And the WebSocket handler is your actual business logic. And the contract is very simple. We're going to use this. We're going to inject our greeting service here, and we're going to write a WebSocket handler. And the WebSocket handler contract is very straightforward. We're going to get a new WebSocket session that's established when the client connects and handshakes with the service. And then with that session on the server side, we can ask for information from the client, or we can send data to the client via the session reference. So we can say session.receive, right? That gives us a publisher of WebSocket message. We can say session.receive.map, WSM.getPayload as text. And we can take that text and turn it into a greetings request. So imagine that the client sends us a name. We want to greet somebody, right? What's the name? That's the parameter that we have in those greetings requests. So I'm going to provide a name, okay? Well, the name is going to come in from the WebSocket client. The client's going to send us a name, just one. It looks like I've got multiple here, but I've just got one. I'm going to take that single name, get the text out of the WebSocket message, turning it into a new greetings request, and then call my greetings service using this new greetings request object. So gs.greet.gr, okay? And once I've done that, I get back a stream of greetings responses. I want to take each one of those streams, each one of those greetings responses, which I'm going to get in perpetuity, one after every second, and then I want to turn it into a WebSocket message. So I say, hey, greetingsresponse.flux.mapgr session.textmessage gr.getMessage, okay? So there's the entire thing. There's the pipeline there. Flux of WebSocket message response. And I got to send that back to the client, and I say session.send. So here I'm reading from the client, and I'm sending a response to the client. Now, normally, I wouldn't tease out these variables as I have here. So I'm going to say var, et cetera, et cetera, et cetera. Okay, there's this, and this one. And we're going to just send the whole thing back like so. Okay, so there's the entire pipeline. This can become a Lambda, of course. Now, there's the Java code. You can see that wasn't so bad, right? This is the sum total of my WebSocket conversation. The exchange between the client and the service is that Java logic there. That wasn't so bad, but in order to demonstrate this to you, I'm looking for the most expedient way to demonstrate this with you, keeping in mind, as I always do, that time is short and of the essence. And so I've struggled long and hard to kind of figure out what I can do to best demonstrate that this works. And I haven't come up with a great answer, so I'm going to do something that I wouldn't otherwise do in polite company, but I have no other way forward. I'm at a bit of an impasse, friends. So I am going to do something that, and again, I'm not proud. Okay, I'm not proud. It doesn't fill me with any pleasure to do something like this in public. But I'm going to write. I'm going to write JavaScript. So a new file, ws.html. Script window.add event listener load function e var ws equals new WebSocket localhost ws greetings add event listener. When the socket opens, I get a callback, and I can use that as a chance to send off requests, including the name to the service. So I say ws.send, and the name will be ATL, okay, or Atlanta Jug. okay? And when the data comes back, I'll log out each record on the console. Well, just whatever, e.data. Okay, there we go. So restart this, take a swig of coffee. Localhost, ws.html. And there you go, my friends. Every second in perpetuity, it's going to produce a new response. You can see it producing that response on the top there. It's going to go on and on and on and on and on and on forever and ever and ever. It has no end. It is endless. It's going to go on and on and on and on. It's like the oceans and the skies and the stars and the bugs in your code. Infinite. Infinite. It's going to go on forever, and that's okay. That's okay, my friends, because when we use reactive APIs, what we're doing is we're giving ourselves the ability to handle more demand. The real win in reactive programming isn't that any one transaction is faster, right? Indeed, because of the context switching that might be happening, which we try and minimize, but it could still happen, because of that context switching, individual transactions might be just that much slower, a sliver bit slower. But we can handle a good deal, many more transactions. That's the win here. We can handle more transactions with reactive APIs. So think about it like this. I use simple math to be able to demonstrate the idea. The goal here is to handle the same number of traffic with half the hardware, or handle double the number of traffic with the same hardware. That's the goal. The goal is not to make each transaction faster. You'll basically be at the same speed, maybe a little bit slower, right? So now that you understand the goal, and what the win is, you can have your data center bill. That's the goal. Put machines out of commission, right? This is a good problem to have. We have gotten to roughly the halfway mark of my little presentation here today. Did you have a question?
Yes. Are you closing the connection here or leave it open?
I'm leaving it open because, the client will as soon as the client disconnects, it'll disconnect on the server side. The browser, as soon as the tab closes down. And you can actually listen to that. You can actually, there's a do on complete or whatever callback, and it'll give you a callback whenever there's a disconnect from the client. And you can tear down any resources associated with that on the server side. So we have now a service. Our service is up and running. It's doing servicey kind of things, right? We've taken advantage of reactive programming to build a single service. But one of the real wins of reactive APIs is when you start to use it for distribution, for building microservices. So in this next 45 minutes, oh boy, we have 40 minutes. In the next 40 minutes, we're going to very, very quickly look at what it means to take these reactive APIs and build microservices, right? We've got a very simple service. This is sort of, Spring Boot day one kind of stuff, but reactive, right? This is all the kind of stuff that you'd want to do for a monolith, put it another way. But now, let's turn to building a client to our little service here. So I've got that. Go back to start.spring.io, and we're going to build a new client to our service. Our client is going to be an edge service. It's going to be a thing that acts as a first port of call for requests coming into the service, or into the system. The edge service is going to be a gateway. It's going to be the thing that routes all the traffic from the outside world to our downstream services. Our downstream services are all going to be fairly homogeneous, right? They're all going to be fairly similar in nature. But we want to be able to adapt incoming clients, iPhones, PlayStations, Xboxes, Rokus, Android devices, HTML5 browser devices, that one person using Windows Mobile, etc. All these things have to be accommodated somewhere, and we can handle that kind of logic at the gateway. The gateway is also a great place to address cross-cutting kinds of concerns like security and compression and routing. So we can do that very naturally. So let's go back to start.spring.io, and we're going to build a new service this time called, guess what? Edge service. I'm very good with the names. And by the way, I owe that to my heritage on the Spring team, right? So on the Spring team, we're famous for being able to name things. We created a framework to support doing MVC, and we called it Spring MVC. We created a framework to handle data, so we called it Spring Data. We created a framework to handle integration, so we called it Spring Integration. We created a framework to handle doing batch processing, so we called it Spring Batch. And we created a framework to handle boots. Oh, wait. Okay, well, anyway, so we're going to build a new service here. I'm going to call this edge service. I'm going to use the latest version of Java because I do the right thing when I can. And I'm going to bring in the reactive web support. I'm going to bring in Spring Cloud Gateway. I'm going to bring in reactive Redis security. What else do I need? Redis security, reactive web gateway. Oh, we want the circuit breaker, resilience for J, Spring Cloud circuit breaker. We want RSocket as well. And I think I'm happy with my selection there. I've got resilience for J, RSocket, Spring Security, Reactive Redis Gateway, and the Reactive Web Support. Looks good to me. Okay, so we're going to hit generate, and that'll give us a new project that we're going to then open up in our IDE, just as we did before. So UAO Edge Service. Now, this Edge Service can handle two different types of work. Two different things you might do in the edge. The one is called an API gateway. API gateways are things that act on incoming requests, but are rather ignorant of the actual payload in the request. They might transform it, they might mutate it, but they don't actually mutate the payload itself. They're ignorant of the semantics or the specifics of that payload. Gateways are great for generic kinds of processing, like compression and security and routing. Okay, so we have a framework that you can use called Spring Cloud Gateway. Spring Cloud Gateway is built on top of a reactive foundation. So it is a natural use case. It's a natural use case for reactive APIs, because the last thing I want to do when I have a gateway, which acts like a proxy, is to proxy a downstream endpoint that's returning 5 terabytes of data, right? I don't want to have to wait till the last byte before I can then send it back to my client. Instead, with the reactive API, I can stream it, right? So I have this Spring Cloud Gateway API. In order to build a Spring Cloud Gateway pipeline, you use the route locator builder. So we say return rlb.routes.route.build, okay? And I'm going to say route spec dot host dot spring.io, okay? And path proxy. So what I'm saying is, when a request comes in to this application, this edge service, this gateway service on port 9999, when that comes in, and if it has a host header equal to @wildcard.spring.io and a path of type proxy, then I want to send it to some other URL. I'm going to proxy it to some other URL. And that service is going to be port 8080. Now, I want to send it to reservations, but I can't do that because consider what I've just said. I've said I want to match the request that has a path of type proxy. Well, I want to send that request unadulterated to the reservations endpoint on the other service, on the other node. But it's already got a path. So what I would end up getting is something like that, reservations proxy. That doesn't exist. So I need to take the incoming request, strip away the path, and then send that down to this other endpoint with a new path, right? So in order to do that, I can use filters. And the filters are really where Spring Cloud Gateway gets a lot of its power, right? So I can do interesting things like, say, set a path, right? Set a path for reservations. There's this, okay? I can set the path reservations. I can do all sorts of interesting things. I can do a redirect. I can do a retry. I can add response headers, set the status code. I can add a response header, HTTP headers, right? Wrong one. Access control allow origin, let's say. I'm gonna allow origin for cores, right? For non-SSL cores, I can do that very generically. All sorts of interesting things that you might want to do there, including circuit breakers, modifying the request and response body, rewriting the path, doing URL rewriting, the kinds of things you might have used Nginx or mod rewrite or Kong for. These kinds of use cases are all well served here. Now, I would use this first, but there are some use cases that are better served by more full-featured API gateways like Apogee, and that's fine. But I would try this first. I'll bet you could get rid of a lot of infrastructure just by using this. So there's a very simple Spring Cloud Gateway path, a predicate. Let's see what this looks like right now. Let's just go ahead and run this first and see what happens. In order for that to work, though, I need to craft a request to HTTP localhost 9999/proxy, and I need to send the host header. So host is going to be equal to atl.spring.io. That's the host header, right? Whoops. Oh, you see the problem? I actually have security on the class path, and so it's blocked that out. I need to actually comment out security for now. Don't try that at home. Okay. Most people just comment it out and forget to add it back and like, oh, it works, and then they go home and then, well, it doesn't work. So Wait, what? Okay. So there's the data, right? If I pipe that out to JQ, you can see I get the JSON data from my service. And I'm getting that data by sending the host data. Let's say I use spring.com, which is not, it doesn't match the path. Then I get 404 not found, right? So it's failing the predicate, right? Okay, so we know that's working. That's good. Well, what other things can I do with these filters? Well, first of all, you should keep in mind that you can create as many routes as you want, right? Route. That's nice. Second thing to keep in mind is that you can actually express these routes in YAML, right? You can actually use the configuration properties to define some of these basic pipelines. You don't have to write Java code. And you can store that configuration in your Spring Cloud config server. And the Spring Cloud config server can then reload stuff dynamically while the process is running. So you can modify these gateway routes without ever recompiling the code, without even restarting the process, right? This is one of the benefits of Spring Cloud Gateway. You can treat it as operational infrastructure or as a library that hangs off the side of your code base in the typical Spring fashion. Either way is fine. Now, I've got this very simple filter here. One of the things I like to use is the rate limiter. Rate limiters are great because they are a way of saying that you want to limit access to the downstream resource, whatever that resource is. In this case, it's my reservation service. A rate limiter is great for two different use cases. One is an absolute aggregate number of people that you want to limit. Let's say that you have a downstream endpoint and it's a very precious, very expensive endpoint. Right? Ignore for the moment that our endpoint is being by my reactive web-based application. It's going to scale. But suppose it didn't. Suppose it was backed by a mainframe. I don't know if you've ever tried to auto-scale a mainframe, but it doesn't do that. It's not. That's one of those tricks that you want to do, and it's a very expensive trick to do if you do scale it out, right? If you need one more user, that's another few $1 million, right? You can do n, but not n plus 1. N plus 1 means new machine. It's very, very expensive. So it's in your best interest to serialize the requests going into that mainframe. Rate limiters are good for that. If you want to limit the absolute number of users going into the system. Hopefully, you don't have that problem. It's 2020. But suppose you do. It's nice to have a rate limiter. Another problem is a little bit more useful in the modern era, which is, hey, I'm not really trying to limit all the requests into my system. I'm not actually trying to say that regardless of who's making the request and where they are and what time of day or night it is, that there's a maximum allowed instance of, let's say, 10 users per second or whatever, or 1,000 or whatever your number is, 1 million, doesn't matter. That's not the actual use case. Much more usefully today, you might want to say, hey, I don't want each individual user to be allowed to make more than 10 requests per second, okay? Now, that's a very different thing. That's not saying 10 requests for the entire planet. That's just saying that you cannot make more than 10 requests per second. And that's just to ensure the quality of service for people using your service, right? You don't want somebody who's abusing your system. Maybe it's a spam robot or something, bot or whatever. You don't want something to take advantage of your generosity and ruin the quality of service for other people on the system. So you can limit them to a number of requests per second. This is a very common thing. So I say rate limiter dot rate limiter. I got to plug in a rate limiter. Now a rate limiter has to keep a count of how many requests have come through an endpoint, and it has to keep that count and then check it against some budget that you prescribe. That budget is how many requests per second you want to allow. Well, where does it keep that count? Let's suppose that it kept a private volatile atomic integer, and it incremented that atomic integer in Java code in memory on the JVM. So I'm saying, let's say for simple math, I'm allowing 10 requests per second, and I've got one node. So in essence, you're allowing 10 requests per second, assuming they all go to that one node. What happens if you create a second node, if you scale out horizontally and have two gateway nodes running on the JVM, running on two different JVMs? Now, since neither one of them knows about each other, and there's no shared state, now in essence, you're actually allowing 20 requests per second per user, right? Because each one of them is going to happily allow 10 requests per second for a given user, not knowing that they've already exceeded that budget in some other node. So this gets problematic. You can't really store that budget. You can't keep that, that tally in Java memory. Instead, it's useful to keep it somewhere that is visible concurrently to all clients, and that's also fast. What's a good fit for that? What data store do you know that has fast atomic numbers? Thank you, exactly. So we're going to use a Redis rate limiter. Okay, return new Redis rate limiter. I'm going to say that I want to have 5 requests per second bursting to 7. Okay, now I'm going to use this rate limiter. I'm going to plug it in here. And there we go. Now Redis is a key value store. It's a distributed data structure server, but it's also a key value store. So in order to access any of the values, you need to know the key. Now the values can be all sorts of things. They can be atomic numbers. They can just be arbitrary blobs and strings and numbers and even queues, right? You can do push and pop on these values. But you still need to know the key by which to access that value. So you need to create a key resolver. So new key resolver. Now this key resolver, again, if I wanted to do that first use case, the mainframe use case, I could say, here's the key. There's only one key for the whole world, right? So I could say, Maria, la chiave. Okay? You ever see that movie, Life is Beautiful? Roberto Benigni? He drops the key from the balcony. The wife of the drunkard drops the key from the balcony whenever he goes, Maria, la chiave, and it comes down. Never mind, it'll come. Anyway, there's one key. That means the entire world has one key, okay? That means I'm limiting the entire world to just, what did I say, 5 requests per second. More usefully though, going to that second use case of I want to limit it per user, I want to examine the incoming request, current Java security principle. We haven't actually spoken about where that Java security principle is coming from yet. I'll talk about that in just a second. Don't you worry. So I've got a security principle in the current authenticated request. I'm going to take the principle. I'm going to say map it to the name. And then for each name, I'm going to use the name as the key. But what if I don't have that name? What if there is no authenticated principle? I'm going to say return. Okay? Very simple. I'm saying my key resolver looks at the current user, and the key is based on the username. So if my username is JLong, then I have a key in Redis called JLong. And JLong can have 5 requests per second. But that doesn't, and even if I use up my 5, that doesn't mean that you and some other name can't have 5 requests per second, okay? So this is a very simple thing to write. You can see it actually boils down quite nicely as lambdas go, right? Very, very clean little thing. It's a very common thing to write, so I'm glad that it's easy to write. It's actually so common, in fact, that we actually pre-wrote it for you, and it does exactly the same thing. Exchange principle, map principle, get name, switch of empty, mono empty. Very, very simple thing to do. It's actually so common, in fact, that's the default. So we can just drop it, right? We're back to where we started. So now the question then becomes, how do we get that authenticated user in the request? And remember what we talked about earlier before. Remember that context for the transaction demarcation that comes into play here. Something has to install the current authenticated user in the current request, which is a reactive pipeline. Who does that? Well, Spring Security does that, right? Spring Security sits as a filter at the front of your application, intercepting requests, and as those requests arrive, it extracts from the incoming request information that it can use to install, to validate the current authenticated identity, and then if it's valid, to install it in the current context so that all subsequent downstream framework code can get access to it, okay? Because I don't want to have to recompute the user each time that request comes in, right? So this brings up another good question. Why don't I want to recompute it, right? And the answer is very obvious. It's expensive. Authentication is expensive, right? Even if the operation of doing the authentication was cheap, you still don't want to have to do it more than once, right? DRY. You want to, for a given request for a single user, you want to do it once and then just reuse that result. It's not like the user is going to become invalid in the next nanosecond, right? It's okay to install it in the current request and then expire it at the end of the request. So that's one point. But think about common types of authentication, right? Authentication answers a very simple question. It answers the question, who is making the request? Is it Josh? Is it Jane? Is it Srinivas? Is it Madhura? Is it Viren? Is it Tammy? It doesn't matter, right? Who's making the request? Is it Josh? Is it Jane? We don't know, right? We ascertain that by extracting information in the current request. Things like session cookies, right? Or an access token for OAuth, or a SAML token, or a X509 certificate for mutual authentication, or a username and password. And there's a lot of different ways to get usernames and passwords. You could have a username and password come in from an HTTP basic form, right? HTTP basic, you submit a username and password. So what happens with username and password based authentication? Let's imagine a very simple homegrown system, ignoring Active Directory and LDAP and all that stuff for now. Let's just say you've got a database table with usernames and passwords in it. What happens when that password comes in from the request? Something has to take that incoming request, that password, and then match it against the usernames and passwords in your database. Hopefully, fingers crossed, hopefully, the passwords in your database are encrypted, right? You don't want to have plain text passwords in your database, right? Right? We're all on the same page about that? No plain text passwords. Josh says, 2020, get rid of the plain text passwords. So you don't want to have plain text passwords in your database. So you take the incoming request, which is coming from the client over HTTPS, of course, so hopefully, but it's still a plain text password. So you want to take that password, you have to then encode it because you want to match the encoding of the passwords in the database. So you encode it. Well, what's a good way to store your passwords today? Spring Security, by default, uses bcrypt. That's a very good, very well-known, well-understood, secure encoding of passwords today in 2020. Who knows though, right? Who knows? Tomorrow, we could get like quantum bcrypt, in which case all the things that we know about security will become irrelevant, right? Happens all the time in the security world, right? Just ask poor old Shaw how it's doing, right? Certain things just don't age well, that's fine. So the state of the art is always changing. That's yet another reason to use Spring Security and to be very, very closely integrated with your security team and your organization. A whole other Oprah though, let's move on. So I need to match the password that's coming in the request with the password in my database. It's bcrypt. I need to take my incoming password and bcrypt encode it and then match that with the bcrypt encoded passwords in the database. Bcrypt takes a little while to do. That's a feature, not a bug, right? It's computationally inefficient. It's going to sit there on the CPU processing the request. It's going to do that encryption on the CPU. It takes a long time. It could take a second. It could take 2 seconds. The strength of the encoding determines the length of the time. Again, a feature, not a bug. Well, this is, again, another example of something that doesn't lend itself to reactive APIs. You can't just rub reactive on it and make it better. It's just going to take the time that it takes. So the question then is, what can Spring Security do in a world of reactive APIs? The answer is, not much. We have reactive adapters, but all that they do is they spin up a new thread, right? It moves the authentication into a separate thread pool that Spring Security uses. So you need to know that that's going to be happening, right? We can't make that thing go away. It's not like we can make that go away. So the question then is, how do we mitigate that? How do we minimize that, right? And the answer is to use something that allows you to exchange expensive long-term credentials for fast short-term credentials. And there's a lot of different ways to do this. The prevailing technology today is something like OAuth. OAuth allows you to say, hey, give me a username and password and exchange it for a token. And then the token, it's fast. You can validate that very, very quickly. It doesn't take a few seconds per validation, right? So using something like OAuth has several benefits. You, first of all, reduce the number of times that you do cryptography, expensive cryptography, to one time in the flow for the user in their current session. Second of all, you excise any of the cryptography from your code base and move that into an authorization server. So now, yes, you have the thing that has to do these expensive encodings, but you can scale that out horizontally without having to scale out the whole system just to be able to accommodate that. And if you are going to have costly, expensive encodings, they're not going to disturb or impinge upon the thread pool that you're using for your mainstream processing, right? The main work that you're doing over here. It's isolated into this authorization server. So it's, not only is it better security, but it's also better performance. And if you go a step further and you pay somebody like Okta or Auth0 or something, now you're basically using your security provider for their CPUs, which is kind of cool, right? And so, just do the right thing for security and let somebody else do it, is I guess my message to you. This is not a message of hope. Security is hard. You're not going to do it well. Let somebody else do it. Just make it somebody else's problem. I'm begging you, please. Don't do security. It's not going to end well. So now, I'm not going to do OAuth because I don't have enough time. And I'm lazy. But you should. So do as I say, not as I do. Or do SAML or something else, right? Just make sure you're not doing usernames and passwords in your request flow for every single request. So in this case, though, I'm going to do exactly that, which is a terrible idea. So I'm going to create a hard-coded username and password database in my Java code. And while I'm doing that, I want to tell you about my friend Rob Winch. Rob Winch is the lead of Spring Security. Okay, he's the lead of Spring Security. And Rob is the nicest guy I've ever had the pleasure of working with. He is in Kansas City, which is another place with great barbecue. And Rob's a very odd cat. Whenever I do this demo, the very demo that I'm doing here with you right now, where I create a username and a password and a role, and then I build the user, I'm creating a hard-coded list of usernames and passwords. Whenever I do this demo, I notice something very odd happens when when I do this demo. I notice something very strange happens. Rob Winch is the lead of Spring Security, so as you can imagine, he's a very busy guy. Lots of stuff to do all the time. Security is a burgeoning field with all these different advancements. He manages a fairly large team working on Spring Security full-time so that Spring Security can be the best framework for security out there for you. And so I noticed something very strange. It doesn't seem to matter where or when I do this demo. It doesn't seem to matter the time zone I'm in. Keep in mind, I travel 650,000 miles every year on United alone, another 100,000 on other airlines, miscellaneous airlines. I visit 30 to 40 countries every year, right? Every year I talk to, let's say 500,000 people, right? Lots of people every year. My goal is to bring spring wherever I can. So I take myself to every corner of the planet, save for Antarctica. Every year, 6 out of the 7 continents, except for Antarctica. And that's because spring's going to be big one day. It's got a future, friends. So it doesn't seem to matter where I am, I noticed. It doesn't matter what time zone I'm in. It doesn't matter what time of day it is for me when I'm doing the demo. He lives in Kansas City, in the middle of these fair United States. And whenever I do this demo, I notice something very peculiar, something very odd. Whenever I do this demo where I have a hard-coded username and password for reasons that Rob Winch can never understand, for reasons that Rob Winch should never understand. Whenever I do this demo using a hard-coded username and password, I notice that Rob Winch, lead of Spring Security, starts responding to messages on Slack. He starts tweeting and sending pull requests. He starts filing issues and responding to things in Google Hangouts. Whenever I do this demo where I have a hard-coded username and password, for reasons that Rob Winch, lead of Spring Security, can and should not ever understand, whenever I do this demo, Rob Winch, lead of Spring Security, becomes sad. And it so disturbs him that it rouses him from a sound sleep. And that's why it doesn't matter what time of day it is. He has nothing, he can't go back to sleep, he's haunted. So he starts working. So I guess what I'm trying to say, friends, is definitely don't do this. Don't make Rob Winch sad. Now, we also have to worry about authorization. Authorization is the act of saying, hey, I know who you are, and I don't trust you in my bedroom, right? Like, I want to server HTTP security, yeah. Okay. So I'm going to limit access to certain parts of the system. I'm going to limit access to certain resources. It's about deciding what rooms are available to you, even once you know the authenticated user. So if you're like an admin, then you have access to everything. If you're just a visitor, then a guest, then you have access to just read-only stuff, for example. So I'm going to say HTTP basic. I want to have HTTP basic. I want to allow that, so that's fine. So I can say customizer with defaults. I want to have an authorized exchange. Okay, so authorized exchange, AE dot any exchange. I'm going to allow it to go through, but I want to limit path matchers. I want to limit proxy. I want to make that authenticated. Okay, and I'm going to disable CSRF. So c.disable. Okay, so there's my authorization. So let's go ahead and restart that. Okay, so now that failed. We can see why. If I go minus V, you can see it says 401 unauthorized. Okay, so now I need to authenticate. So I can say -u JLong PW, and there's the data, right? Let's look at the headers though, minus V. And as I do that, you can see it's giving me the rate limiter headers as well. It's saying that, hey, you've got so many tokens in the token bucket left over before you exceed your budget. So now we can drive that. Let's drive it with a ad hoc load balance, right? Like this. So as I do that, I'm just doing a while loop. I'm looping over and over, just an infinite loop. I'm just saying while true, and then I'm calling curl, and I'm making requests to the system, trying to exceed as best as I can that rate limiter's permission. I'm getting a 429 whenever I exceed the budget that I've been given. Okay? So the rate limiter is protecting that downstream service. Hopefully, you've got a cloud platform that's going to spin up new instances, and you'll be just fine. But you want to make sure that that downstream service is fine. So now we've got a gateway. Spring Cloud Gateway can do plenty of other tricks, but we have to move on. Another thing that you might want to do at an edge service is an API adapter. API adapters act on the data that they are given. So here, this is just a simple router function. So we say server response routes, and I'm going to create a simple endpoint that is going to give me a view on the data from the downstream reservation service. So I'm going to go to the edge service /reservations/names, and I'm going to use that endpoint to make a network call to the reservation service on port 8080. In order to do that, I need to create a reactive HTTP client. So I'm going to inject the builder here, return builder.build. I'm going to inject my reactive HTTP client to make this call. So here we are, HTTP. In order for this to work, I'm going to say server response.ok.body. I'm going to make a call to the downstream service. So http.get.uri http localhost 8080/reservations.retrieve, and I want to take the JSON that comes back and convert it into a reservation. So now I need to do something terrible, something that you should never ever do ever, not even when you're all by yourself at home and no one is looking. I'm going to copy and paste code. So here we are. Where's my reservation? Good. Copy pasta. Paste. Good. All right, so this is my DTO, my client-side representation of that type. I'm going to say turn it into a stream of type reservation. There's my reservation stream, reservations. And I'm making a network call across the wire using HTTP. I'm assuming that the data will come back and I'll be able to use it. It's going to give me a stream of reservations. But is that always going to work? Is the network infinitely fast? Is that always going to be, the result that I want? Will it return in time, right? So maybe what I want is actually just the names, right? So there's the names. I'm going to map it to a string. But even there, that cannot work all the time, right? Things are going to fail. Depending on the scale that you've got, eventually, something will always be broken, right? So we need to build a little bit of robustness into our code. We can do things. I can say, okay, on error, resume. So when there's an exception, I want to return a fallback value. Eek, okay? So I control how I degrade. It doesn't return exception on the wire. I back rather than giving them a big Java stack trace or a 500 error. Okay, that's one thing you can do. You could also tell it to retry. You can say, hey, retry the request if it fails, or retry it 10 times, or retry it 10 times, and each time wait 10 seconds, or wait a second, right? Right. So you have some options there that you can use. Timeouts are also an option. You can say timeout duration of, 1 time unit second, whatever. Right, you can do that. But I'm not a big fan of timeouts. Timeouts are a last resort, surely. What you're trying to do here, think about timeouts. What you're trying to do here is you're trying to say, hey, I want this response within a certain budget, a certain time, an SLA. And the reason I need this is because somebody else is depending on me to provide within a certain SLA. So let's suppose that my SLA for simple math is 10 seconds. Okay, requests are a lot shorter than that, but let's say it takes 10 seconds to produce a response. But I need to call another service. So what is the budget I need to give? What is the SLA, the timeout for that service in that request to be? Realistically, what should it be? I'd say 5 seconds. because that gives me at least one more chance to try again if something fails, right? But what about the poor service downstream that service has to second, right? So that it has a chance to retry. And then the thing after that, what about that? Now you're 4 levels in and your window is getting vanishingly small. Timeouts are restrictive. It's a very passive-aggressive thing to do to your neighbors. So I wouldn't recommend timeouts, and they don't actually solve the problem either. You've only bought yourself one more chance, right? Much better to have a much bigger, more eggs in the basket, so to speak. And so what high-performance websites do is something called service hedging. Hedging is, like in investing. You don't put all your eggs in one basket. This is a common aphorism that we all know about, right? You don't put all your money on red in the casino, right? These very simple idea, right? Very simple thing that we all know about. Well, in service hedging, what you do is you call and deployed across discrete nodes using Spring Cloud client for service. It's a way of contacting a service registry like Console or Zookeeper or Netflix Eureka or whatever, right? Cloud Foundry, Kubernetes all can act as service. And you're asking them, you're saying, hey, instances of the service. It's the same in host 2 and 3. Let's say it's on host 1 through 10, but I only need, let's say, 3, okay? Doesn't matter, just 3 unique instances. I don't want host 1, 2, and 3, or host 2, 3, and 5. So now I've got 3 different instances. I want to launch the same request to all 3 of them in concurrence, in flight, at the same time. And whichever one produces a response faster, or fastest, that's the one I want to keep. I want to discard the other one, apply back pressure to the other ones, because I don't need them. Of course, this only works for use cases where the call is idempotent, right? I want to do this on the charge the customer credit card endpoint. This only works for things where you can do it without undue observable side effects. But it's a very common use case. Google does this, Netflix does this, Uber does this. They do it all the time. And it's a very easy thing to imagine, but it's actually really hard code to get right if you had to write it yourself. In the reactive world, though, it's very easy to do. So let's suppose I have call 1. I'll leave it to your imagination to reproduce the call that we just did up here, right? Let's say I've got call 1, call 2, and call 3. Now remember, I haven't actually, again, nothing actually happens on the wire until you subscribe. So even though I've defined these 3 pipelines, let's say that I've got these, let's say that these are not null. Let's just imagine that I've made a call to host 1, host 2, and host 3. Even if I've defined all 3 of those, I don't actually have anything being sent over the wire yet. And so what I can do is I can say, okay, I want the fastest one. So I can say call 1, call 2, call 3. And that'll give me the fastest pipeline. And whichever one emits a value first, it'll keep and it'll apply back pressure to the other 2 automatically. So that pattern that would have been really hard to do, had you to do it by yourself in threads and phasers and cyclic pairs and countdown latches and executive services and runnables and all that nonsense, all that code that you would have had to write to do this becomes a one-liner. Now, this is very important here. Using reactive APIs, you take advantage of the API, you take advantage of the framework and the operators to write reactive code, to write concurrent code much more efficiently, much more safely than you could otherwise. Remember, there's only one person who truly understands how to write effective multi-threaded Java code, and it's not you. It doesn't matter who it is, it's not you. That's the point, friends. So just use the framework. Let it do the work for you. You'll get to production faster and your code will be safer and better. So, okay. Now I've got a simple call here. I'm calling the downstream service. One thing that we could also do is use a circuit breaker. A circuit breaker goes one step further. It keeps a state table. The state table says, hey, there's a flag that says this pathway, this call, this network, this path here has failed before. And so it'll short circuit the attempt to make that same call again because it sees the flag has been raised and it says this is and it's impassable, right? That flag is independent of this code. It lives somewhere else in memory. And so other things, other Java threads, other processes, whatever, can come along and say, okay, I'm going to change that flag back to green instead of red. Because I know that if this thing tried the attempt again, it would work. So circuit breaker is really great if you have a use case for a call that you know will fail, right? This code right here it's naive, regardless of any external circumstances. It doesn't know what we know. We could look at our service registry and go, oh, hey, of course that's going to fail. There's no running instance of course it failed. But this code doesn't know about that. The circuit breaker can know about that, right? Something could monitor the service registry and then reset the flag in the circuit breaker state table. It could say, hey, don't even bother, just short circuit it, fail fast and let the client move on. So circuit breakers are a really awesome next step. But as I have only got 3 minutes, I want to just turn now to one last thing. I've been talking to you about HTTP because, frankly, HTTP is too big to ignore, right? It's out there. I think it's got a future. It could be a very good document retrieval protocol one day. I don't think it's a particularly great platform protocol. And so a lot of organizations are of the same mind, right, of the same opinion. So Google created gRPC, for example. gRPC is a slight improvement, but it's still pipeline multiplexing, and it doesn't address a lot of common use cases. So what I want is a protocol that allows me, it's payload agnostic, so I don't want to have to use Google protocol. I want to be able to support all the different common message exchange patterns, so request response, fire and forget, directional communication, multiplex communication. I don't want to constantly hack and connect, disconnect. I want to be able to keep stateful connection open. That's multiplex, so I can all the network connection setup and dismantling. And I want simple things like headers. Like WebSockets don't have headers. How are you supposed to propagate out-of-band information like a security token without a header, right? This is very, very simple, obvious stuff, right? But it's not there. So I want all these things in a protocol. And HTTP and all this, bread and butter. It's not the use case for which that was designed. And it's clearly lacking in these basic use cases. Not to mention, it's very efficient, right? It's text, it's porous, right, by default. So Facebook created a protocol called RSocket. RSocket is a binary protocol. It can do all the things I just described and so much more. It's a protocol. So once either side connects to the other one, no longer client service, they're request or repeat. And either side can initiate the discussion as long as they want. So now, what I'm going to do very quickly in my last waning minutes with you here today is turn my ever so humble greetings service here into an RSocket service, right? So we're going to say greetings service. I'll say at controller. I'll say at message mapping greetings. Okay? And in order for this to work, it needs to serve on a port. So I'm going to use RSocket server port 8888. That's good luck in Chinese. So I'm going to use that. Happy Chinese New Year a couple days from now. So there we go. Start that up. And now on the client, I've got no time at all. So the client, I'm just going to create a simple consumer RSocket client consumer. And it's just going to be a Spring Bean that listens for the application ready event. Ready. And in order for this to do its work, I need the RSocket requester. And you create the RSocket requester just like you create the HTTP web client. Okay, so I'm going to inject that into the constructor there. Add required args constructor. And you go up here and you build the RSocket requester. So the RSocket requester has a little bit more to it than the HTTP client because, of course, we have to connect, right? So we have to connect to the service to which we're trying to make these requests. Builder.connect TCP localhost 8888.block. Okay. Once that's done, I can now say this.RSocket requester.route greetings. Okay. And I want to take the data that's coming back. Remember, the data in this case is of type greetings response. So I'm going to do copy and paste just as I did before. Okay. And greetings response, request rather. And we're just going to log out the results. So I'm going to say retrieve a flux of greetings response.class. And we're going to send some data in, a new greetings request. RSocket for the win. Fans in ATL, okay? And then for each one of those results, I'm just going to log out the results. So we'll say system.out print line. There we go. Restart. There we are, my friends. We're using RSocket to create a reactive stream. That's what that is. It's a reactive stream. You can see I can subscribe to it, but up until here, I have a flux of greetings response. I'm creating a reactive stream using a binary protocol to talk to the service over the RSocket port. This is not HTTP, but I can use it with, I can take that RSocket reactive stream, and it's a publisher of type T, right? It's a reactive stream just like we've seen before. I can then send that to a WebSocket client or send it back to an HTTP response or whatever. In this case, though, I'm just printing it out because I don't have a lot of time. Because everything is a publisher and the world truly is asynchronous by default, it becomes very easy to plumb together these different things that don't otherwise relate to each other because they're all just publishers, right? You can use the reactive APIs with Kafka and RabbitMQ. We have a reactive Kafka and RabbitMQ client. You can use these reactive APIs with web and WebSockets and RSocket, and we have support in Spring integration for this as well. You can actually use reactive endpoints in Spring integration. So these reactive APIs give you the ability to take inherently asynchronous things and tie them together. You get more elegant code. You get an API that allows you to describe the actual fact of the uncertainty of these APIs, the fact that things are going to fail over the network. You can deal with that here with Reactor, and you get better efficiency. It's a win-win all around. And I've written less code. Look at that example with surface hedging. Try writing that code with the equivalent Java threading code. You're not going to like your result, and you're going to be a drunk at the end of it, right? A lot of alcohol required. All right, my friends, I hope you got something out of this. I hope you learned something. I certainly love this stuff. I'm a big fan. First of all, who learned something new? Good stuff. Who had fun? Good stuff. I'm glad there's a mostly overlap there. There's two people that seem very unhappy. Probably him. I love this stuff. Obviously, I love this stuff. I'm a big fan. I'm wearing the Spring t-shirt, the Spring underwear. Big fan. I'm a big fan. I love this stuff. And I love this stuff because I know that organizations, large and small, all around the planet are using it to great effect. I mentioned some of the names that are already out there using this stuff to great effect. There's Netflix, right? Facebook is the company that created, by the way, the Java binding for RSocket, this binary protocol I just talked to you about, created at Facebook, uses RSocket, right? So the RSocket technology, it uses Reactor. It uses Pivotal's Project Reactor for the Java binding for RSocket at Facebook. Netflix is using this stuff, right? There's a small company in China called Alibaba. Anybody know about them? They're going to be big one day. They're a small company. I visit Hangzhou in China. They're about an hour's train right away from Shanghai. I visit them every year. I go spend a few days at the campus in Hangzhou talking to my friends at Alibaba. And every year I've gone to them. In 2015, I went to them and said, hey, my friends, we've just released this thing called Spring Boot. You've got to see it. Because they've been using Spring. I've been talking to them since 2012. They've been using Spring for at least the last 10 years. More than that. Everything in Alibaba, Alipay, Aliyun, AliCloud, Taobao, everything is all Spring. Now, it's increasingly more and more Spring Boot. And then more recently, Spring Cloud. And now, Reactive. And now, RSocket. So now, Pivotal and Alibaba and Netify are the first fledgling members of the Reactive Foundation, the first project of which is RSocket. Launched this joint initiative last year, right? A new foundation just around Reactive. So these are large players on the internet that have the smart people. They could do this stuff themselves. They could build it themselves if they needed to, but they choose to use the Spring and VMware stack because they know that it allows them to build better software, to get to production faster and safer. And at the end of the day, that really is all that matters. Thank you so much, everybody. Cheers.